Okay, here we go. We're going to talk about Chapter 8, Section 1 today. Just a quick note, I did not get the worksheet assignment to go along with this to you on Tuesday, so I'll get that to you on Thursday when you come back. But you can download it at the bottom of this page and work on it if you would like. It should follow right along with the notes I'm giving. There's a warm-up question on it and practice problems on it that I'll go through as well. So without further ado, here we are. Warm-up question number 1. A baseball is hit 1 meter above the ground with a velocity of 40 meters per second and an angle of 45 degrees. The ball lands in the bleachers 5.1 seconds later. How far away from home plate did the ball land? Well, let's go ahead and start with what we know. We know that we've got a ball hit at an angle. So that means we got to have a triangle for that. The angle is 45 degrees. Our initial velocity, which is the hypotenuse, is going to be equal to 40 meters per second. We need to find our VIX. Okay, so in order to find our VIX, it is just, this is a review, so hopefully you remember. Remember, since it's on the bottom, that'll be the cosine. So 40 meters per second times the cosine of our angle, which is 45 degrees. And that should give us a value of 28.28 meters per second. Okay, now in the problem, we are just looking for how far away from home plate. That is going to be a dx. So we actually don't even need our VIY here. So we just have to solve for dx. dx, remember our formula for that is equal to VIX times time. So we go 28.28 meters per second times the time given in the problem of 5.1 seconds. So dx equals 144.25 meters. So that was a good old throwback projectile problem from earlier in the year. Hopefully that went okay with you. And you will go ahead and move on from there. Okay, Chapter 8 is fluid mechanics. We'll be talking about buoyancy, like our duck here. We'll talk about pressure and how it relates, like in a hydraulic lift, and how it relates in a hose and moving pressure and that sort of stuff as well. So in this first section, we're really going to look at doing a couple of things. We're going to define what a fluid is, be able to distinguish between a gas and a fluid, determine the magnitude of buoyant force. Okay, that'll be our math component. And we should definitely be able to explain why some objects float and some sink. Okay, a quick review. You guys should remember this from 5th grade and definitely from 9th grade. Matter. What is matter? Matter is anything that has mass and takes up space. Matter is pretty much everything. Everything is the matter. Haha, punny. Anyway, there are 3 different states of matter. Those are solid, liquid, and gas. Those are our 3 states of matter. Now, since we're talking about fluid mechanics, we need to distinguish between a fluid and a solid. A fluid is a non-solid matter whose atoms or molecules can flow freely, so they can move very easily. There are 2 types of fluids. They are gases with 2 S's, I think, and liquids. Those are our 2 types of fluids. Now, there's a difference between a liquid and a gas. A liquid has a definite volume. Okay, gases have a definite volume. Okay, what I mean by that is in the objects or in the drawings down here, you can see that a liquid, if you put a liquid in a cup, you cannot compress it very much. Okay, it's going to take the shape of its container just like a gas, but you cannot compress that liquid. A gas, however, if you put a gas into a cup, you can compress it, make it smaller, whereas a liquid has a definite volume and a gas does not. Okay, now density is another important thing we're going to talk about as we get into buoyant force here. Density is the measure of something, anything really, but like people in these examples, in any given space. Okay, the density in this mall and on this beach is very, 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 very high. there are a lot of people in the given space. The density here, which is where I would rather be, is much, much lower. Okay, there actually are no people in this picture for the given space that is shown. Okay, so density is just how much of something there is in any given area. Okay, don't worry if I'm going kind of fast. You can review this at any time. You can pause at any time. So don't hesitate to pause. I also will have the PowerPoint saved online, so you can go back and view that without having to listen to me talk if that's helpful to you as well. Okay, so density and buoyant force. Again, density is just how much matter there is in certain space. Mass density is a more scientific term for that. Um, and our equation for mass density, or density as I will call it, is this goofy little symbol here, which is called rho. Okay, that is rho. Looks like a P. Density is equal to mass divided by volume. Okay, mass divided by volume. Our units for density are going to be a kilogram per meter cubed. Kilogram per meter cubed. There are some densities that you'll be given in the problems that we're doing. One density should definitely your memory somehow. That's one that'll come up a lot, is water. Excuse me. So again, density is mass over volume. The units are kilograms per meter cubed. The density for water is 1,000 meters cubed. Okay. Now again, solids and liquids are nearly incompressible. Okay, that's why they have a definite volume. Gases, however, can be compressed. That's why we get things like compressed gas in tanks, like these here in the center. That's why they usually have a gauge on here. Um, they can be compressed and their densities end up changing depending on what kind of pressure they're under and what kind of temperature they're under. So the density of a gas is a little bit trickier to find, but the densities of solids and liquids are pretty definite. Uh, I don't know what would possess a person to do that, but that doesn't seem like a very good idea. Kind of funny though. All right, now on to the good stuff, buoyant force. Okay, buoyant force is an upward force exerted by a liquid on an object, immersed in or floating on the liquid. Okay, it's important to understand that whenever an object is in a fluid, okay, whether that's a gas or a liquid, there's a buoyant force acting on it. Even if something sinks, okay, like if you drop a rock to the bottom of a lake, there's still a buoyant force on it. That's why it feels lighter when it's under the water. Okay, because there's still a buoyant force acting on it, even though it's not enough to sink it. It's also important to remember that buoyant force is always an upward force. It always acts up against gravity. Okay, it always acts up against gravity. So if we were to draw a vector diagram for our aircraft, the Italian cruise ship that ran aground and ended up sinking. So the gravitational force acting on this cruise ship is larger than the buoyant force acting on the cruise ship. That's why it's not floating, whereas the aircraft carrier is. Okay. The Titanic, not exactly a very strong buoyant force after it hit the iceberg, which is why it sunk. Um, yeah, not very unsinkable. Okay, so density and buoyant force continued. This gentleman named Archimedes, he actually is sort of the guy that came up with the idea of this buoyant force. His principle says that any object that is in a fluid, okay, whether it's completely submerged or not, experience an upward buoyant force equal in magnitude to the weight of the fluid displaced. Equal in magnitude to of the fluid displaced. Okay, so basically buoyant force is equal to the weight, which is force of gravity, of the displaced fluid. Okay, is mf, acceleration due to gravity. Okay, so buoyant force is equal to the weight of the displaced fluid. Um, it's important to sort of remember that this mf here, all right, you can solve for mass based off of our density equation. Okay, that object's density, that same amount. Okay, that's an important substitution that we will be using later on. So keep that in mind. Okay, it's important to understand that you can get this mass by substituting. Okay, again, displaced fluid basically is how much liquid would be there if the object was not put there. So the object number 1 here, the brick is not in the water, so there's no displaced fluid. Object number 2, with it halfway in there, there is a certain amount of water that is displaced, and then number 3, there is even more water that is completely submerged. Okay, now whether an object will sink or float depends on the net force acting on the object in the fluid. If the buoyant force is equal to the gravitational force of the object, then the object is going to float. Okay, think about that. Makes sense, just like with the aircraft carrier. Remember that the volume quantities are referring to the amount of fluid that is displaced. Okay, whether or not an object is completely submerged doesn't necessarily matter, because the volume of the object that is in the fluid is going to equal the volume of the fluid that is displaced. So if the volume of the object, V sub O, is equal to 16, then the volume of the fluid displaced is also equal to 16. Okay, volume is volume is volume. So whatever amount of the object is in the water is going to displace that same amount of fluid. All right. So keep that in mind when we are working through these. That kind of brings us to a good point. The aircraft carrier. Aircraft carriers are made of lots and lots and lots and lots of steel, and steel is much more dense than water. So how then does an aircraft carrier float? Good question. Well, the answer, since I'm not going to get anybody to answer in here, is an aircraft carrier displaces a very large amount of water. Okay, the water that is displaced is very great, and when you look at the total density of the aircraft carrier, there's a lot of air that's inside the aircraft carrier, or any ship for that matter. Okay, any boat, any boat that's in the water displaces a lot of water and is also filled with air, which is less dense than water. Okay, now the cruise ship here, or the Titanic, as it started to sink, it filled up with water. And as it's filling up with water, the gravitational force keeps getting bigger and bigger and bigger and bigger. And the buoyant force gets smaller and smaller and smaller and smaller because there's less air that's in there and there's less water that is displaced. Okay, so that's how objects made of very dense materials like steel are able to float, because they displace lots of water while filling it with airspace. But as soon as that airspace gets filled in with water, then obviously there's an issue. Okay. Now, when an object is completely submerged, there's what's called the apparent weight of that object. Okay, the apparent weight, that's why objects that are submerged in the water feel lighter. That's why a heavy rock in the water feels lighter while it's underwater, but then if you get it out of the water, it is much heavier and you might not be able to lift it at all. Because when it's under the water, there's still a buoyant force pushing up on it. The buoyant force, again, is equal to the object's, is equal to the mass of the water displaced times gravity. Okay, so it still holds true. Now this ratio right here can be very helpful to solve for an object's density while in the water. This only works when it's submerged, however. Okay. Couple of practice problems to try here. Again, this is right on your what we're going to have to figure out here, first of all, is the buoyant force. Now, buoyant force is equal to the force of gravity um, minus the apparent force, or excuse me, the apparent weight. Okay, remember that apparent weight is what it feels like when it's submerged in water. Okay, it's going to be less than the actual weight. It's going to be less than the actual force of gravity. So we got that information in our problem here. The weight, or the force of gravity, is 7.84 newtons. That's its actual weight. And we're going to subtract the apparent weight when it's in the water, which is 6.86 newtons. Okay, so our buoyant force is going to equal 0.98 newtons. Okay, that's the amount of force the water is pushing up on the crown with. Okay, now in order to figure out what the density of this crown is, so we can compare it to gold's density, we are going to use that ratio. We know the weight, force due to gravity. We now know the buoyant force. Okay, we are looking for the density of the object. That's an O. And we know the density of the fluid. Okay, it's in water. Remember that number I asked you to write down? We know that the density of water is 1,000 kilograms per meter cubed. So let's go ahead and plug our numbers in. 7.84 newtons over 0.98 newtons is equal to the density of an object divided by 1,000 kilograms meter cubed. Okay, all we have to do is solve for rho O, that's weird, which gives us a value of 8,000 kilograms per meter cubed. Okay, so now the question is the crown made of pure gold? Well, the density here is 8,000. The density of gold is 19,000. So no, there's no way that crown is made of gold because the densities are way different. Okay, I got another practice problem here for you. A ferry boat is 4 meters wide and 6 meters long. When a truck pulls onto it, the boat sinks 0.04 meters into the water. What is the weight of the truck? Okay, now in order to solve for this, let's start by finding the volume of our object here. Okay, the volume of the object, remember, is going to be equal to the volume of the fluid that is displaced. So in order to solve for that, we're going to go 4 meters times 6 meters times 0.04 meters. Okay, make sure you're remembering a little bit of geometry here. Okay, so that gives us a volume of 0.96 meters cubed. And then since our object is floating here, we know that the buoyant force is equal to the gravitational force, or the weight. Now we're trying to find this, the weight of the truck. Okay, stay with me. Remember that buoyant force is equal to mass of the fluid times g, acceleration due to gravity. But remember, we can substitute that m for the volume of the fluid times the density of the fluid times g. Okay, so we now know all of these values. So we just got to plug everything in. VF is right here, 0.96 meters cubed. We know density of water, again, is 1,000 kilograms per meter cubed. And we also know the acceleration due to gravity is still always 9.81 meters per second squared. That value will give us a force due to gravity, which is the weight of 9417.6 newtons. Okay? And again, you can always check units. I know this seems like a crazy unit here, but if you look, meters cubed is going to cancel. You're left with a kilogram per meter per second squared, which is in fact a newton. Okay, that is our first lesson. Sorry if it was a little bit long, but this PowerPoint will be on my website as well. You can use this stuff to help you on the questions on the worksheet. I'm also going to ask you to follow along with a part on the website. It asks your worksheet asks you to go to your book website and go to the animated physics section. Okay, so when you go to your book website, make sure that you put chapter 8 in this box and section 1 in this box, and then go to the animated physics section and click on this right here. Okay, and if you follow right through there, there's a good animation lab that you can use. It'll help. It follows right along with the lab questions in there for you as well. Okay, give it a shot. If you have questions, we got class time to check it out. All right, thank you very much.